Hi there. Just in case I have you confused, I wanted to try to make one video addressing this idea of differentiating whenever you have two variables. So, we've been seeing things like this, or ddx of y to the fourth, or something like that. And it doesn't have to be t or x. Okay, so I'm going to show you an example where, oops, I made a typo there. We might have something like ddp of x to the third. So I realize you have some conflicting information, and I think you are starting to get it, but I want to make sure we understand whenever this kind of thing is zero, or if we use the chain rule. And that's the idea about what we're trying to get at here. Now, one thing to realize about the form of all these is, remember, this is considered the independent variable in each one of these, all right? And so there's our independent variable. And then we have a dependent variable, a possibly dependent variable right here. But we don't just have the variable, we have a function of the variable. Okay, so I'm hoping this notation, I've been struggling with the right kind of notation to use for this video. But the idea here is that if I want to talk in general, what we're doing is we're taking the derivative with respect to some independent variable. So I'm going to use I. All right, I want to use D here for dependent variable, but we already have D used. So I'm just going to say V. Leave a little bit of space if you're writing here. V. But the key thing is, we're not just differentiating the independent or the dependent variable. We're differentiating a function of the dependent variable. So we have to say f of v, like that. Okay. So I hope that that doesn't confuse you, but that's the best I can come up with to illustrate this. And then again, the question is, is that derivative zero, or do I use some chain rule idea, at least behind the scenes? Okay, so where the confusion possibly got started is when we first started talking about derivatives. And I gave you no other context. I would just give you a problem that looked like this, okay? And I didn't say anything else about it. So if you have no other context given, then if you're looking at this kind of thing right here and you're not given anything else about it, you're not told anything else about it, then you're treating this as a constant, all right? And same thing here. If I didn't tell you anything, then then you just treat it as a constant. So in these cases, if there's no other context given, you do treat that as a constant, and so all these derivatives are zero. So, and that's the thing. At the beginning of the course, I didn't give you any other context, and so we treated those as constants. All right. Now, what's different and what we've been seeing lately is we are given some context that either implies, the problem might say that the sides of a rectangle are changing in time, or there might be information given implying that it's changing in time. The length is changing at, 5 meters per second or something like that. Then you have some kind of context telling you that that dependent variable or that second variable does depend on your independent variable. All right. Then what goes on? Then we're going to use the chain rule. Okay, it's just, this notation's already confusing enough, and then we got to add in more parentheses. The reason we're using the chain rule is now we have a function of that independent variable right there, and so that implies that we use the chain rule. And so then, in general, what you would do is you would take the derivative of the outside, that would be the f prime of v, but then you would multiply times the derivative of the inside. Your derivative of your inside is that v of I right there. I know this looks confusing right here. All right, like that. But that's the idea. And the key thing is what you want to distinguish between is if you're given no other context, those kind of derivatives would be zero. But if you're given context that something is a function of something else, then you apply the chain rule. So then going through those three examples right there, if you're told that b is a function of t, then this ends up being a chain rule. Now I'm going to show you the short way and the long way. You can help. All right. So all that complicated notation means is you just take the normal derivative. You don't worry about all this chain rule stuff. So if I just ask you what the derivative of b squared is, you'd probably say 2b. All right. And then you just multiply times the just the general Leibniz derivative. So your dependent variable, which would be b over dt. Okay, and so without all that notation, if I have this, then I would just quickly write 2b db dt, like that. Now, if you're still having trouble understanding why this is going on right here, what you do is, since you're told that b is a function of t, you could replace b by itself with b of t to emphasize that dependence on t. Okay, and so here I have a chain rule. My outside is the squaring function, and my inside is just that b of t. That, so if I apply the chain rule there, I would differentiate the outside like that, but remember we leave the inside function alone at first. Like that. That's a first power. Let me stress that that's a 1. Okay, but then you multiply by the derivative of the inside. We don't know what b of t is, but we can denote its derivative as b prime of t. Okay, like that. And then we can take out all these parentheses and emphasis on the dependence on t, sorry. So that really this right here is all just saying 2b to the first, so 2b times b prime. You could still use b prime if you remember that it's a time derivative, or you could really emphasize it by using the Leibniz notation. Same thing here. If I tell you that y is a function of x, now this is that dependent variable, that v that I was talking about. So if you need to, you could think about this as being d dx of y of x to the third. And there your outside function is the cubing function, and your inside function is y of x. All right? But the idea here is how do we differentiate that outside function? We do 3 to the squared, like that. But what is my inside function? It's y, like that. And then we multiply times the derivative of the inside. The inside is y, so we get dy dx. So the idea is, you can really clutter things up doing this, but if it helps you, go ahead. I'm not saying don't do it. But the idea here is that if you have something that looks like this, where you have two different variables, but there's some kind of context telling you that this is a function of this, then what you do is you just take the normal derivative, what you would think is the derivative of y to the third, okay, 3y squared, and then you just multiply by d of the dependent variable over d of the independent variable. So dy over dx. But what you're really doing behind the scene is the chain rule. Okay? Now there could be all kinds of other dependencies. Time and x are the two most common ones in an intro calculus class. But if you think about this, this could be the volume of a cube. So we could have some cube here, like that, and then some kind of pressure is being applied to the sides of that cube. So this thing could at times deflect out or deflect in, all right, and like that. And so anyway, the idea here is, don't worry about that. I just try to think of something with a different dependence than what we've seen. But we're told that x is a function of p, so what do? Hopefully this is sinking in by now. And so you just do the normal derivative. What do you think of as the derivative of x to the third? 3x squared. But then you multiply by d of the dependent variable over d of the independent variable. So that would be dx over dp. And so this derivative would be 3x squared dx over dp. All right? So I hope that makes sense. And then again, on this problem, if I just wrote this, but I didn't say anything else, so ignore all that stuff up there at the top. If I just said, what is this? And I don't give you any other context, you say it's 0. But if I say x is a function of t, of p, like that, then whenever I do this, then it becomes 3x squared dx over dp. All right. All right. Hope that clears things up.